Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying differentiability lecture 3 and this is the last lecture of differentiability. So we'll be talking about standard derivatives and functional equations in this lecture. Okay. So let's begin our lecture with the derivations of few standard derivatives using first principle. So we'll be talking about sin x and ln x and their derivatives. Okay. So what is first principle? First principle is f dash x plus basically Rational derivative, that is limit h approaches 0 f of x plus h minus fx divided by h, right? This is our first principle. And if you want to write f dash x minus, that would be limit h approaches 0 f of x minus h minus fx divided by minus h, right? So when both of them are actually equal, we say that derivative is existing for that function at a particular point, right? Now, if we talk about sin x, we'll be writing derivative first. That would be f dash x plus equals to limit h approaches 0 sine of x plus h minus sin x divided by h, right? Now, this is sin c minus sin d. What is sin c minus sin d? Sin c minus sin d is 2 cos c plus d by 2 dot sin c minus d by 2, right? So let's write that. So we have limit h approaches 0 to cos of c plus d by 2, that would be x plus h by 2 dot sine of c minus d by 2, that would be h by 2, right? Divide by h. Now this looks like standard limit because h is approaching 0, right? So that's why this looks like standard limit, but we don't have h by 2 over here, so let's create that. We'll be multiplying and dividing by 2. Now this 2 gets cancelled out and this becomes the standard limit, right? So this becomes limit h approaches 0 cos of x plus h by 2 dot 1, because this is 1 only, right? Standard limit. Now, if we talk about this particular limit, that would be cos x only, right? Because x is approaching, h is approaching 0. So this becomes cos x. So we know that derivative of sin x is cos x. We won't be calculating f dash x minus because that would yield the same result. So we have just calculated right hand derivative, that is f dash x plus, and we've got to the outcome that derivative of sin x is cos x with the help of first principle, right? Now let's talk about ln x. We have f dash x plus equals to limit h approaches 0 ln of x plus h minus ln x divided by h, right? Now we'll be using the log property over here. Limit h approaches 0, this would become ln of x plus h by x, right? Divided by h. Now this can be written as 1 plus h by x, right? Now this again looks like standard limit. So what we'll be doing, we'll be multiplying and dividing by x to create the perfect standard limit, right? So this limit actually becomes 1. This is 1. So our final outcome becomes 1 by x. This is 1 by x over here and this is 1 over here. So final outcome is 1 by x. So derivative of ln x is 1 by x. And now that we have seen how to derive derivative of a particular function with the help of first principle, you have to remember all of these. You don't have to rely on the derivation part. Derivation part was just to make you understand the concept, but you have to remember all of these derivatives by heart. And same goes for these ones, right? Now let's move on with functional equations. And sometimes we see equations like f of x plus y equals to fx plus fy. And then we kind of intuitively know that the function might be a linear function, that is kx. And similarly, if we have f of x plus y equals to fx dot fy, then we might know that the function is exponential function intuitively, right? And similarly for this log function and this power function, right? But in most of the cases, you'll not be able to guess the function just by looking at it, right? Intuitively. For that, we need a proper method. So now let's derive the first one, that is f of x plus y equals to fx plus fy. But you must be wondering, why are we studying this in differentiability lecture, right? Because we are going to use the first principle method to derive these functions out of these functional equations, right? So we have f of x plus y equals to fx plus fy. This is what has been given. Now the inherent assumption over here is all these functions are differentiable. Remember that all these functions are differentiable. After that, we'll be starting with right hand derivative. That would be f dash x plus equals to limit h approaches 0 f of x plus h minus fx divided by h, right? Now we have f of x plus y over here. We have f of x plus h over here, right? So what we can do in this one, I'll be replacing x with x only and y with h. Okay. So this becomes f of x plus h equals to fx plus fh, right? So we'll be using this one over here. So this becomes limit h approaches 0 f of x plus fh minus fx divided by h. Now this and this gets cancelled out. What we're left with? Limit h approaches 0 fh by h. Now understand one thing, that when are we going to get an output from this limit? We are going to get an output from this limit only when fh by h turns out to be a standard limit, right? So this gives me an idea that I might write this as f of 0 plus h divided by h, and I somehow want f of 0 over here, so that this can turn out to be f dash 0 plus, right? F dash 0 plus would be same as f dash 0 because the function is differentiable. So f dash 0 plus would be same as f dash 0, and f dash 0 would be a constant number, and I will be able to integrate this one. I'll be able to integrate this one when we have a constant number over here or some kind of output over here, right, based on the standard limit, right? So this is the basic idea. So what we can do, we can write this as 0 plus h minus f of 0. I'm just writing it over here as of now. It doesn't make any sense, right? We'll see if we have to remove this or not. Now, first of all, we need to find out the value of f0, right? So if I plug in 0 in there, what I'll be getting? F of 0 plus 0 equals to f0 plus f0. That gives us f0 as 0 only. So that makes perfect sense, right? Because we had nothing over here. So I wrote f of 0 over there. Now this becomes f dash 0 plus, which is nothing but f dash 0 only, right? Until now it's very clear. What we have done, we have started with first principle, then we used this equation over here in there, and then cancel out fx. What we are left with fh by h. Then we somehow manipulated it to write down f dash 0 from there, right? The main element was to find out the value of f0, and sometimes you might have to find out the value of f1, f2, f3, whatever. But the thing is, you have to find out those values only for which we are targeting f dash. We were targeting f dash 0 over here, so that's why we found out the value of f0. If we were targeting f of 1 plus h in that case, by any chance, then we would have targeted f of 1 over here, right? But in this case, we wanted f0 over there because that made perfect sense for this to become f dash 0, right? Now f dash 0 is nothing but a constant number, let's say k. Okay, so ultimately what we've got is f dash x plus equals to some k constant. Now f dash x plus would be f dash x only because the functions are differentiable as we have discussed the assumption. So f dash x equals to k. Now if you want to integrate it, we'll be getting fx equals to kx plus c, right? C is the constant of integration. Now if you put x equals to 0 over here, we'll be getting f0 equals to k into 0 plus c. That gives us c equals to 0. Okay. So basically that means fx equals to kx. So this is the derivation for this particular functional equation. Basically we have derived that function, this function particularly satisfies this functional equation. Okay. You have to follow the same process for all the equations over here. Now let's solve this question. Let fx be a differentiable function satisfying f of x by y equals to fx minus fy for all xy bigger than 0. If f dash 1 equals to 1, then find the value of fx. We'll start with the same process once again. We'll start with right hand derivative. That would be f dash x plus, that is limit h approaches 0 f of x plus h minus fx divided by h. Now we have f of x plus h minus fx over here. And what do we have? We have fx minus fy. Something similar, right? So what we'll be doing, we'll be utilizing this over here, right? So we can, in this equation, we can replace x with x plus h and y with x. Okay, so that becomes f of x plus h divided by x equals to f of x plus h minus fx. We'll be utilizing this over here, right? Now this actually becomes limit h approaches 0 f of x plus h by x divided by h, right? Now we can write this as f of 1 plus h by x divided by h, right? Now in the previous example, we had f of 0 plus h, right? That's why we were so determined to find out the value of f of 0, because that would have made perfect sense, so that this entire equation becomes f dash 0 plus, right? Similarly, we have f of 1 plus h by x over here. So I must be determined to find the value of f of 1. I should have f of 1 over here somehow, out of nowhere, right? So let's try to find out the value of f of 1. So f of 1 by 1 equals to f of 1 minus f of 1. Basically putting 1 for x and y in this equation. Okay. So that gives me f of 1 as 0. And that makes perfect sense, right? Because we had nothing over here. We had 0 over here. And I wrote minus f of 1. That is again nothing. But this equation becomes much more favorable as compared to the previous one, right? So basically, what we have got, limit h approaches 0, f of 1 plus h by x minus f of 1, which is nothing but 0, divided by h. Now for this to be a standard limit, right, for this to be a standard first principle derivative, we should have h by x and h by x on both sides. Basically h by x is nothing but h dash, right? This is nothing but h dash. What we have written over here, we have written 1 plus f of 1 plus h dash minus f of 1 divided by h. So to convert this h into h dash, I'll have to multiply and divide by x. Now this becomes h dash, right? Now this becomes the standard limit, which is nothing but f dash 1, right? So basically this becomes limit h approaches 0, 1 upon x dot f dash 1 plus. And now we know that the inherent assumption over here is all these functions are differentiable. So I can write f dash 1 plus as f dash 1 only, right? Same thing. Now f dash 1 is given as 1. So this is nothing but 1. Now what we have got, 1 upon x into 1, limit h approaches 0. So this comes out to be 1 by x only, right? So what we have eventually got is f dash x equals to 1 by x. Now let's integrate this. We'll be getting fx equals to ln x plus c, because integral of 1 by x is ln x, right? Now to find out the value of constant c, we'll be putting x equals to 1 over here. We'll be getting f of 1 equals to ln 1 plus c, right? Now this is 0. This is also 0, because we found out the value of f1 is 0, right? This is 0, this is 0, so c also 0. So basically we have got fx equals to ln x, right? So based on these two examples, you must have got a little understanding how to solve these type of questions. Ultimately, you have to use the given equation and first principle and club them together and do the manipulations, right? This is how you have to solve all these questions. So today's lecture was till here only, and this marks the end of differentiability. From next lecture onwards, we'll be starting with methods of differentiation and AOD, right? So let's meet in the next lecture. Thanks for watching.